Hey, my name is Andy Soffer. I work at Google, and I'm going to be talking about a project that I worked on for about 1.5 years. I came in at the tail end of this project. A lot of other engineers worked on this for many years before I even started on it. This one's particularly fun for me to talk about because I actually said something like this: how hard could it be when I started on this project? And so today we're going to explore a few of the things that make this an interesting project, make this sort of difficult, and some of the things that you might not expect to make this a difficult problem. And with that said, let's dive right into it. Since we're talking about integers, might as well review what those are. So in C++, there are these 10 types that we call the standard integer types. There's signed char, short, long, int, long, and long, and then the unsigned versions of all of those. And our problem actually starts right here, right? The standard guarantees surprisingly little about what these are and what they could possibly mean. For us, the most important property that the standard talks about is that of bit width. So this is what bit width is. This is probably familiar to most of us, but we're going to go through it. So bit width tells us which integers we can represent, right? Integers are a mathematical concept. There are infinitely many of them, but computers are a little bit more finite than that, and so we can't represent all integers. We're going to restrict ourselves to those that we actually that we can fit in a certain size. And bit width tells us what that is. A bit width of n means that there are 2 to the n values that we can represent, and these are the values that they mean, right? So if you have an unsigned number with bit width of n, it means you can represent the values from 0 up to, but not including 2 to the n. And if it's signed, then you sort of have that shifted, so it's roughly even between, you have roughly the same number of negative numbers and positives. Can't be exactly the same, you gotta have 0, so we have one more negative number. But these are the values that you get. When I first started learning C++, I was told that an int is 4 bytes. And it can hold value from -2 to the 31 up to 2 to the 31 minus 1. But that's not the whole story, right? That was probably true on whatever platform I was working on the time, but it's not guaranteed at all. Here's what the standard actually guarantees. An int needs to have a bit width of at least 16, and it's often 32, but it could be 20, could be 471. Like those are all perfectly reasonable bit widths. So what do we do, right? I have some numbers I want to represent. I roughly know like the range of the values for the numbers I'm talking about in my program. What type should I choose, right? I don't know that any of these is going to necessarily be large enough. And because it depends, you end up writing code like this, right? It's not defined by the C++ standard, but you end up writing things that check your platform. If I'm on Linux and it's x86 64-bit, then long is going to be a 64-bit integer, and so I can define int64 to be long. If I'm on a different platform, maybe I use a different type. But I sort of figure this out by asking the platform I'm on. Now, today we're just going to be focusing on one platform, and it's a pretty common one. We're going to be talking about x86 architectures, running Linux, being compiled with either Clang or GCC, and using those standard libraries. There are tons of other platforms where the same problems come up, but I want to focus on just one today because it's already hard enough if we're just talking about a single platform. And so our story actually begins with a file that sort of looks like this. I'm going to focus in on just a small section of it for just Linux x86. It's a file that sort of looks like this. So the year is 1999. Google's a small company with about 40 employees, and these type defs are added into our code base. As I mentioned, on different platforms there might be different definitions, but we're sort of focusing on one today. And I think the main takeaway I want you to have from this slide is that there's nothing incorrect here, right? Like all of these type defs that are here are correct. They were correct when they were written. They're correct today, right? Int really is a 32-bit, has bit width 32 on the platforms we're talking about. Long really is 64 bits on the platform that we're talking about. We're going to fast forward a little bit, and in 2011, we get these typedefs in standard C++. They've been in C for a while, but they're sort of codified into C++ in the C++11 standard. And this is really fantastic, right? These sort of they do the same thing as the typedefs that we've had in our code base for a while, but they're standardized. And this is great because it means that we can more easily take our internal code and make it open source, right? We can more easily take open source projects and rely on them internally, because if we share these things. And it's a small thing, but for new hires, there's a lot to get them up to speed. And if we just take this like one thing that they don't have to learn anymore, like that's a win. It's a small win, but it's still a win. Right? There's less for people to learn. So this is our goal, right? We want to delete integral types.h, that file I showed you, and we want to use the standard. And once we've done that, we get all of the benefits of using the standard library. But we can't just delete integral types.h. If we do that, like everything's going to break, right? Everything depends on this. It's the very bottom of the stack. So if we're going to do that, we first need to change every use of int64 in the entire code base to be int64_t. And we can't just do that. We also need to replace all of the includes of integral types.h to be c_studint, the header that the standard defines. And if you've seen talks by Hiram Wright or Titus Winters, you know that like Google has a lot of practice making these changes, right? The idea of like a global find replace across our entire code base isn't something we're particularly afraid of. It helps that we have like a monolithic code repository. We can actually see all of the code all at once. But this is where things get tricky. We're well practiced at find replace when the changes we're making have no semantic effect on the code. What I mean by that is if we're just renaming a function, right? It's the same function body, but we're just renaming it. We know how to do those. Or we're renaming a class. Anything that's a drop-in replacement is pretty easy. So our actual first step towards this ice cream party is to ensure that int64 and int64_t are the same type, right? We know that they're aliases that are going to have the same bit width, because that's what the 64 means, but they may or may not be the same type. Once they're the same type, that's how we know that they're drop-in replacements for each other, and the rest of this follows. And in fact, this is the only thing we're going to be talking about today. The rest of the steps here, in particular 5, are fascinating and like really, really interesting. And there's whole talks about the rest of this, but we're not going to go into that today. It's just this first step that we're going to be talking about. So let's actually take a look at the aliases. We know the standard doesn't guarantee that they're the same, but maybe they end up being the same anyway, and we're just going to get lucky. That would be a kind of a boring talk, I suppose. But here's what the definitions we actually see. Right? So we saw integral types.h already, and we know that from there, int64 is a long. But it turns out in c_studint, again, on the platforms we care about, right? Linux, x86, using Clang and the standard library there, int64 is an alias for long. And if these were the same, we'd have a drop-in replacement. It would be a relatively easy, if still long process to change, but that's not the case we're in. And so this is what we're talking about today, right? This one-line change, not even one line, right? This is a 4-character change. How hard could this possibly be? Before we dig into all of the reasons why this is actually like really hard, I want to take a moment to put you in the mindset that I was in when I asked this question. So I'm going to go through all the reasons why this is actually like a really easy thing to do. Right? So for starters, these types are interconvertible, right? And implicitly so. They represent the same range of values. I'm not going to end up with any truncation or narrowing or data loss when I convert between them. We already know they're the same size, right? They're both 8 bytes. They have the same alignment. And beyond that, like the bit representations of these two things are absolutely identical. They're so identical, like processors don't even distinguish between values of the same thing, right? They're like totally identical in terms of what the processor thinks about. So now that I've tricked you into thinking that like the talk is basically over, I want to actually show you why this is hard. But I don't want to be just a downer about it, right? That wouldn't be particularly fun. So I want to try to understand what makes this a difficult problem and how we can reduce the cost of similar problems in the future. So as we look through examples of these problems that we encounter, I want you to have the following 3 questions in mind. And we're going to sort of go through examples and continue to revisit these questions as we see the examples. So first, what went well, right? Like some of the things went well, and where is it clear that like our decisions or the processes that we had actually made things go easier than they could have been if we made different choices. Secondly, what went poorly, right? What did we miss in terms of either technical changes or policy or procedure that we could have followed that would have produced a better outcome and made this easier? These are the things that we really want to do for next time, right? The changes and improvements we want to make. And lastly, where did we get lucky? This one's kind of speculative, right? It's an attempt to guess about the things that might go poorly next time if the circumstances are similar. But I think this one's really important as well. If you've recognized these questions, it might be because you've read the SRE book. These are the questions you typically ask when you're conducting a postmortem. And we're not really doing a postmortem here today per se, but I think these are really useful questions regardless, for learning from any experience. Before we get started with the examples, I want to address a particular question that comes up really frequently. And that's, if you look at this plan, why do we bother starting with step 1, right? I can just start changing things from int64 to int64_t in step 2, and most of the time it's going to work, right? Most of the time we're not going to run into the problems that we see. And this is a fantastic question with a really subtle answer, right? Because either way we do this, we're going to end up with the same outcome, right? We're going to end up using int64_t everywhere. It's going to be an alias for long, and we're going to get our ice cream. So why does the order here that we do these things matter? And the answer to that question is, suppose we started at step 2. We started changing int64 to int64_t. In a large code base, this is going to take a long time, right? Google's got about 250 million lines of code. That's not a change we're going to make in a day. That's going to take weeks, months, maybe a year or two. And as we get through there, like let's say we get halfway through, and then we find out actually this is really difficult. In fact, it's so difficult we're not going to be able to do it. We can't afford to do it. Or maybe it's doable, but it's just our priorities have changed, and we can't do it right now. In either of these situations, we're in this state where our code base is sort of half converted. It's half int64, it's half int64_t. And what do we do about that? Do we convert back? Right? We already know that conversion process took a long time, and do we really want to go through that effort of converting everything back? Like that doesn't seem right. If we leave it there, what guidance do we give to developers? Like which one should they be using? Do we prefer the direction we want to go? Do we tell them to sort of match the existing thing in the project they're working on? These are the sorts of questions that are really difficult. And we want to avoid having to make a decision here. On the other hand, if we do all of the work up front to make these types as compatible as they need to be, if we change the definition of int64 to match that for int64_t, if we get halfway through and we realize yeah, this is too difficult, we've basically made no user visible changes, right? We can just stop and no one will know, other than me, that we did all this work and then we decided to change our mind. There's not significant impact to our users. And so that's why we prefer to make the types the same first. And so with that, with all that said, let's get started with, why is that not, there we go. Let's get started with a warm-up. Let's talk about references, right? So throughout this, I'm going to show you some snippets of code, and we're going to think about like, how is this going to break when we change the definition of int64 from long, what it was at the beginning, to long afterwards. So here's our snippet. We've got a class. It's got this get value that takes a reference to a long. It's gonna fill in that with the value, and then we've got some function takes a widget, and we pass an int64 n in on line 8. So remember, this is compiles. This is sort of supposed to be indicative of code that exists in our code base when we start the project, when int64 is an alias for long. And we're changing int64 to be an alias for long. So show of hands, who can see how this is going to break? We've got like a few hands. So we're going to try it and see what happens. This is the error message that Clang gives us, right? It says, non-const L value reference to type long cannot bind to a value of unrelated type int64, aka long. And it gives us the line where this is happening. And the point here is that, like I said, long and long are interconvertible, right? And implicitly so. But references to them are not. Right? I can't use a reference to a long when I need one for a long. Pointers are going to have the same problem here. And so this happens from time to time in the code base, and we need a fix for it. And so this is the ideal fix, right? We're just going to change the long to be int64. The reason we like this change is because, well, our style guide is pretty clear about preferring int64 over long or long. And the reasoning for that style guide choice is, well, int64 tells you how big it is, right? It tells you the information that you want to know. Long, as we learned, like doesn't tell you any of that information. The other thing that's nice about this change is, right now when I change the definition of int64, whether it's long or long, these are going to match, right? As I change it back and forth, the references will be able to bind to each other just fine. But it's not always this easy, right? What if get value was a virtual function?
I have a quick question. So
yeah, sure.
And what if someone was passing a long straight into that? Maybe I just don't know how C++ works there.
If someone was passing a long
into get value, and then you change it to int64.
So if I'm understanding the question, like if instead of on line 7 it said int64n, if it said long n, yeah. So that would break if we made this change, right? I'll get to that. That actually happened a couple times, but like very infrequently. And I think that's one of the things that went well. So yeah, fantastic question. We'll get to that in a couple of minutes. But that definitely would break. This is another situation that we ran into that was actually really tricky, right? If get value is if it's virtual, then suddenly I don't just have to worry about this one call to this function. I have to worry about, right, if I want to change the definition of get value, I need to change it on widget base as well. And not only on widget base, but on every class that derives from widget base and all of the places that those call. Right? Suddenly what we had that was like a small local function change becomes this massive thing where I have to worry about an entire class hierarchy. And like, thankfully, while this did happen, this was actually pretty rare. And so fixing these by hand was just like entirely reasonable for us to do. So, okay, this is the first example. What went well, and this gets to Zola's question. I think the real star of this story is the style guide, right? All of the situations that I showed you, they happened, but they were really rare. And that's because we had pretty solid adherence to the style guide. It's pretty well enforced. And this addresses Zola's question because like we didn't see long for a variable very often. It's forbidden by the style guide. You should always be writing int64 instead. And so like, it happens a little bit, it happens in third-party code in particular, but it was not a particularly frequent occurrence. Another thing that went really well here is that code owners are actually, they were really receptive to change. We've really heavily invested in the idea that everyone at the company has a sort of joint ownership over the entire code base. And so when I sent out changes for people to review on their code, things that I didn't really interact with particularly much, people were really receptive. They said, like, yeah, like this is a thing we need to do. Happy to help review and get this submitted so we can get this change sort of, for the health of the entire code base. But not everything was smiley faces, right? Virtual functions were like a real significant pain here. We have refactoring tools. I'll talk about those a bunch later on, but none of them were particularly helpful for virtual functions. Virtual functions were really just a matter of elbow grease. This is also a space where we got kind of lucky. There weren't a lot of them, so it wasn't like super painful. And I think that this is a place where we got lucky rather than something that went well, because I actually have no reason to believe that in the future for similar problems, we aren't going to have large class hierarchies. Like those are things that happen in our code base just as everyone else's. And I haven't done any of like looking at the numbers, but I suspect if we're talking about changes that aren't about integers but are about, say, strings, there are going to be a lot more virtual functions and like class hierarchies that have strings as parameters. And if we had to change something like that, this would have gone much, much worse. Now, I said we want to be thinking about for places where we got lucky, like how are we going to address this in the future? I have no idea, right? I'm not here with all the answers. Maybe some sort of automated tooling to detect these, but like that's really hard and sort of beyond what we can do today. But food for thought. So I'm going to move on to the next thing I want to talk about here, which is overload resolution. And in particular, I want to talk about templates. So here's a function, clamp above 0, right? It takes int64n, and it's supposed to return 0 if the thing is negative and the number otherwise. Again, this works fine when int64 is an alias for long, long. We're going to change it to an alias for long. Anybody see what goes wrong here? Yeah, okay, a few more hands this time. This one is kind of weird, right? Like just looking at this function, I can't really see entirely what's going on. I have to actually look at stdmax and know what happens there. So here's what stdmax might look like. The body of the function isn't important. What is important are the parameters, right? I've got a function template, and it accepts the left-hand side and right-hand side as references to constant t's. And the important point here is that they're actually the same t, right? The types are the same there, and the type deduction algorithm puts them on equal footing, right? Neither can be preferred over the other because they're identical here. If we look back at our example, when we're calling stdmax, when int64 is an alias for long, long, we're passing in a long, long on the left, and 0, the LL suffix means that it's also a long, long. But when we change int64 to be an alias for long, suddenly they don't match anymore. And we can't figure out what the template parameter should be, right? Should it be long? Should it be long, long? It's unclear. And so this is a problem that we encountered thousands of times. I think it was less than 10,000, but like this came up definitely thousands of times. And so like, what do we do, right? Like I'm not gonna spend my wrists on fixing something manually thousands of times. So we're gonna use automated refactoring tools here. But what change do we want to make? There's a lot of options for how we can change this. And so one kind of tempting example, one tempting solution is this, right? We can explicitly specify the template parameter. And this is kind of nice, right? I don't have to use the suffix for 0 anymore. Like 0 by itself is fine. Because what's happening here is that 0 is an int, but we're passing it into this function that accepts an int64, and so it will be implicitly converted to to an int64 before we call this function. And that actually is sort of the problem, or at least the concern. When you explicitly specialize template parameters like this, you're effectively working with a normal function, and all of the normal implicit conversions apply, not just the good ones. I don't expect somebody to pass in true like this, but I didn't want to, not just we didn't want to sort of introduce the possibility for these implicit conversions throughout the code base at scale, right? If you're doing it in a couple cases, maybe it's fine, but we didn't want this to be a thing that someone was able to copy and then change some parameters and oops, like we've given them another footgun to use. So we didn't choose this approach. We chose to make the changes like this, right? By brace initializing the 0 as an int64, we know we're going to get the right type. We're still using type deduction, but now when we change int64, the types always match. And so this will call a different stdmax instantiation, but it'll still do the right thing. So this is the change we made. We wrote a clang tidy check to sort of run throughout our code base, find instances of this pattern, fix it like this, and this resolved most of the issues. We had to do this for stdmax, for stdmin, lots of functions like that. But it's worth asking the question, why was 0LL in the code base in the first place, right? The style guide is pretty clear, like we don't want to have the, we don't want to use long explicitly. Why was that even there? And I'm not positive about this, but my best guess is that people originally wrote stdmax of n comma 0, and that failed to compile. And it mentioned something about the types don't match and something about you should be using a long. And the shortest solution to write is to add LL at the end there. And that's really unfortunate, right? That's a diagnostic trying to be helpful and leading engineers to do the wrong thing. I don't think that's anyone's fault in particular, but it is sort of an unfortunate situation that arose. Yeah, Titus.
I also suspect that we never got the linkers to diagnose the LL suffix.
Yeah, so Titus's comment is that we have linters and that we probably didn't get the linter to diagnose the LL suffix. That might be true. We should probably do that. Yeah, we should probably do that if we're not already. Yeah, so changing it up a little bit, I've got a sort of similar function here, right? I've got this function template, compare. Again, same pattern. It's going to take const ref for both parameters, so they're on equal footing. We're going to see same sorts of problems with type deduction, but I'm calling it in basically the same way. But I left some space here, and so I'm going to throw a little wrinkle in, and here's that wrinkle. I don't know why you would have a compare overload for two bools, but this was in our code base, right? This is like real code, and it's things that we have to deal with. So now, show of hands, who sees what's going to go wrong here? Okay, so we only have Richard Smith for the record. So yeah, again, this is something that actually showed up in our code base. I think this particular problem only showed up like once or twice, but it was definitely there. And the horrifying thing is that this calls the bool overload. So why what's happening here, right? So just as before, when we change the type of int64, the template parameters don't match, right? And so we can't call that one, but there's this nice thing where substitution failure isn't an error, right? That's just silently thrown out, and we try other things. And hey, look at that. Long and long both implicitly convert to bool. And so the second overload on line 6 is the only correct match, and so we're going to call that one. And if you think about this, this is wrong in a very subtle way, right? If value is negative, that negative value, when converted to a bool, since it's not 0, counts as true. And so when I ask, is my negative number greater than 0, I'm comparing 0, which is now false, to this negative number, which is true. False is less than true, so yeah, my negative number is greater than 0. So this is terrifying. So okay, like let's go through our questions again. What went well here? What went wrong? So again, Clang tools I think are the real star in this example. Being able to write your own Clang tidy checks, not just the ones that sort of exist in the ecosystem already, but to write your own is a superpower. And being able to run them over your entire code base, find all of the problems in your entire code base, like that's a huge superpower. And it made this actually feasible to solve, right? If we weren't able to do this in an automated fashion, looking at all of our entire code base, this problem would have been entirely untenable. The second thing here that went really well is unit tests. We've got a pretty strong culture of unit testing. And it was a unit test that caught this Boolean overload, right? Like that's not me reading through all of our code and just sort of guessing at what's gonna happen. A unit test failed. And that actually highlights a really important thing about unit tests, right? They're really useful for making sure your code today does what you want it to do today. And even that your code works tomorrow as well, right? They're sort of protection against time. But they're also protection against me, right? When I go and change what int64 means, these subtle things can happen, like these subtle breakages can happen, and they give you some assurance that we're gonna catch some, probably not all, but we're gonna catch some, most, hopefully most of the issues. And so like the unit test that ended up, somebody passed in a negative number and the test failed, and like good on them for writing that test. One of the things that went kind of wrong was diagnostics. They led engineers to write these anti-patterns with 0LL. That's not the thing that we want to have in the code base. To be clear, I don't think the diagnostics themselves are to blame. I think it's writing a diagnostic is very is difficult. You're sort of catering to a very broad audience, and you don't know what code they're writing. And I don't think the engineers who are interpreting it are to blame either. It's just that the combination of the two, of the messages that they provide, along with a code base that discourages spelling long, sort of lead people to writing these anti-patterns. This can be solved with a Clang tidy, but what I really would love is sort of scriptable diagnostics, right? Being able to plug into your compiler and say like, hey, I would like this sort of a message. I'd like it to reference our style guide and like tell people that like these are the things that that they should be writing. Another problem, like overload resolution is just really, really complicated. After going through this sort of stuff for like a year or more, I kind of have some ideas about some best practices on how to write overload sets, but I don't think it's reasonable to expect most engineers to have figured out these sorts of things. That's just, it's just too complicated, and it's a thing I really wish we could fix. So moving on to the next section, right? This is a talk about integers, so let's talk about the most integer-y thing we can think of, strings. So I'm going to be talking about this function, string printf. You probably have something similar in your code base. This is pretty much like printf, except it doesn't print the string to standard out. It writes it to a std string. So all of the things that we're going to be talking about here like apply equally well to printf. It's just sort of easier to show and talk about if we're talking about string printf. Does anyone see the problem here? What's going to go wrong? Got a few people, Titus, who I think originally showed me this problem. So here's the error message we get, right? Format specifies type long, but the argument has type long, and it's if you have to pass this warning flag W format to get these, but it's the same sort of problem we're seeing over and over again. Right? Where we're changing the definition of int64. So it's changing the type that we're talking about, long versus long, but we've hard-coded one of the types. Previously we were hard-coding it with like the suffixed integer literal, but here we've done it in the format string, and we've asked for format string checking, and so it checks it. So this is a problem that showed up, like string printf is a function that's used several 100,000 times in our code base. So we're not fixing this one by hand, right? There's just that's entirely out of the question. We're going to be writing, use automated refactoring tools, but the problem is actually slightly larger than this, because you can ask for format, format checking for any function. It doesn't just have to be like string printf or printf. You can add this attribute anywhere, and you can actually add it on virtual functions. And so all of the problems we talked about with virtual functions at the beginning, like, I have to change these simultaneously, like those all apply. I think there were 20-ish of these in the codebase. I don't remember the exact numbers, but like not many, but each of them is actually quite painful to work through. And we just did, right? Like this was just by hand, like a lot of elbow grease here. These actually aren't the examples I want to focus on. The really fun stuff is the stuff we ended up using automated tools for most of it. And so I want to focus on like the automated change we made in the common case. And so this is what we did. We actually invented our own printf, right? Absol_stir format is a replacement for string printf, and it works basically the same way, but it doesn't care about the %ll. In the format specifier, you can just use %d. And this is really amazing, right? Because now if we're using this function, if I'm switching between long and long, long, I don't have to change the format specifier. It figures out the type, right? You'll see it's a template, and so it's deducing the type from n as it's passed in, and we know how large the value needs to be if we're going to print it by deducing it from the type. This is actually like one of my favorite APIs that we have in Absol, and it's great for a lot of reasons. Some of them actually have nothing to do with int64. We decided to change our entire code base to use this over string printf, regardless of whether or not we were passing in int64, because of all of these benefits. So here's another example of where it might be used. You have string printf, and you're printing out something about this puppy class, and you can't pass into printf or string printf a stood string directly. You have to call .cstir on it, which is a little bit annoying. But we can, with absol_stir format, we can just pass in a string, right? Or a string view, or a const char_star. Like those are all fine, and all of this just works. And so we decided to make this change because this is just a straight up better API, and we want that improvement for our users. And honestly, how hard could that be? So this error message at the bottom, error undefined symbol puppy k cuteness, is probably the most confusing error message I have ever seen from any tool chain, right? Like I'm looking at the definition right there on line 10. What do you mean it's not defined? So this showed up hundreds of times as we're making these changes. And the problem here is actually not visible on the slide. It's a combination of some pretty esoteric language rules and the definition of absol_stir format. So here are the definitions, or at least the signatures of string printf and absol_stir format. String printf looks largely like printf, right? It takes a const char_star for its format string, and then C-style variadic arguments. One thing to note about variadic arguments is they're always passed by value. And that's important here. Stir format, on the other hand, this format spec thing doesn't particularly matter, but the important part is that the arguments are passed by const reference. And it's important that they're passed by const reference, right? We said that they take strings directly. We don't want to be copying the string every time just to read out of it. We really want to be passing those by reference for performance. But herein lies the problem. Right? Like I'm going to show you, I'm not going to show you the issue with the esoteric language rules of the standard. Like I know we all have the standard memorized anyway, but the relevant section is this basic def ODR paragraph 5. And roughly speaking, it says that if you're going to pass a variable by reference, it needs a definition. Okay, that makes sense. Initializing a static inside of a class doesn't count as a definition. I'm not totally sure why this is the case. There are experts that I'd actually like to know the answer from in the audience. But there's one more bit here, which is that if the variable is constexpr, not just const, but constexpr, then this doesn't count. And this does count as an inline definition. And so that's our fix for this linker error, where we don't have a definition here. What we're going to do is we're going to change it to be constexpr. And this is another thing that we wrote a clang tidy check for. We ran it over our code base, and now we're catching these problems not just the one time, but we catch them any time that somebody writes static const int something. Like we suggest that it should be constexpr, like as part of code review. So once again, like thinking back to our questions, clang tools were immensely helpful here, right? Like I can't stress enough how amazing it is to be able to inspect your code and find problems like very early on. This was really instrumental in making this manageable at all. On the flip side, like language rules are just like baffling, right? Like this is very confusing. I don't intend this to be a dig on like the standards committee at all. This rule might have a good reason that I'm not aware of. And if it doesn't, like there's just so much work that needs to be done. It's just, there aren't enough people to do all of that work. And either way, like it's not their fault. But regardless, there's complexity here, right? And it's harmful to developers. I imagine that this is a problem that other people encountered as well. If before I went and changed string printf to absol store format, I imagine that other people saw this better API, attempted the change, got a very confusing error, and didn't have the time to look into it. And so they just said, okay, I guess we're not changing this one, and we're going to stick with the worst API. This really does harm developers in that way. Another problem is like, yeah, we're missing a definition here, and we identified it really late in the process. What I mean by that is you probably always want definitions for your variables. And we didn't actually find out that we were missing a definition until this thing became ODR used, right? And it would be really nice to identify those earlier, and that's what the clang tidy check does. But this is a thing that I suppose we could have done in the language or in the compiler and let people know even earlier. And of course, I can't really give a talk without mentioning Hiram's law, right? No one promised that string printf wasn't going to ODR use its arguments, but when you have a few 100,000 calls to a function, like somebody's going to end up relying on the fact that it worked that way. And this is exactly what happens with Hiram's law. We got really lucky on this one also. Most of our format strings were checked at compile time. If we didn't have that, we wouldn't have had a particularly robust way to verify that our changes were safe. We would have gone through and made these changes, and they wouldn't have been checked, and that might have introduced undefined behavior into our code base. In practice, I think this is undefined behavior that's like probably fine. Like I don't think there are any optimizations that are really going to take advantage of this one, but I'm really not willing to make that bet with a few 100,000 of these, right? Like that's not a safe bet. So I got one more thing I want to talk about today, and this one really blew my mind. It's about performance, right? So this is the change we're making. Remember, I said processors don't distinguish at all between these two types. Like these are going to generate the same assembly code. So you'll be as surprised as I was when we got all this working, everything compiled and linked, all the test pass. And we ran some performance tests, and we found a 2% performance regression. This totally blew my mind when I first learned about it. How could this possibly be, right? These are absolutely identical. And the answer is this thing called profile guided optimization. The idea here is you've got your code running in production, and you've got you're taking profiling samples as it's running. And you're going to use those samples to gather information and pass them into the next version of your binary and use those to optimize, right? So for every function that you see that you're calling, you write down some performance-related notes, and then when you go to recompile, you have all this information about that function, and you can use it to improve branch prediction, cache locality, like any number of other things, anything that you can optimize about your function. So before we make this change, we see functions like the first one, right? My function takes a long, right? int64 is just an alias, so the type that's really underlying that is a long. And then we change it, and we have this totally different function, my function that takes a long. And all of the profile-guided optimization tools that we have, right, say like, okay, well, these could be different functions. I don't actually know that they're the same. So all of this information I gathered about the first function, which apparently you deleted, I can't use for this other function, my function of long. So I'm just going to throw out that data. Right, so we had all of this performance data that we could have used, and we just threw it away. And that's where the 2% performance regression comes from. It's the fact that we were doing optimizations, and then we stopped doing them on the subsequent version. So there's a pretty easy fix for this in Clang. Clang has this flag, f profile remapping file. You can give it a file that sort of gives it instructions about how to do remappings between functions. And what I mean by that is you can tell it, my function that takes a long, yeah, that's the same as my function of long. Don't worry about it. Just use the profile from the first one on the second one. Everything will be okay. So you can do this not just for like two functions specifically, but you can say anywhere you see a long as like a function parameter, you should treat that as the same as a long. And this brought that difference back down to 0. So that was really nice. Another thing that went well here is that the testability, right? It's absolutely crucial that we can test this before we get to production. Like a 2% performance loss on something as large as web search is a really big number. It might seem small, but it's like that's a lot of compute resources. One problem here, though, is that we were actually really not able to explore this early. And what I mean by that is what I would have wanted to do is know before we actually went through all of the process of making these changes, I wanted to know what the performance cost would have been, right? I'm not able to measure that until my code compiles, and my code's not going to compile until I basically fix all of the problems in the first place. I think a tool here that could be helpful is if we could selectively throw away a bunch of performance information, right? If we could say anything you get from a function that takes a long, like throw away that performance information and see how much worse it's going to perform. That would give us sort of a proxy for how much this profile remapping would help. One thing that went where we got lucky is institutional knowledge, right? I actually had no idea that this was a thing I needed to think about. One of my coworkers just pointed out, like, hey, you should measure the performance of this thing. And I don't know what would have happened if they hadn't said that. Hopefully somebody else would have caught me, but like, it's not written down anywhere. And another thing, like, what if this didn't work? This profile remapping is a really great tool, but it's possible that like there were two functions that took a long and a long that really had different profiles, and they needed to. Like that was important for performance. And that when we do the profile remapping to make them the same, that could actually be a performance regression. Thankfully that didn't happen, but I don't see any reason why that didn't, and I don't know what we would have done in those situations. So sort of wrapping up and talking about the lessons we learned from all of this, I think there are sort of three major themes. The first, right, change is inevitable. Hiram Wright of Hiram's Law likes to say that you will eventually want to change every single line of code that you have ever written. And I think this is like really well exemplified in this particular problem, right? What could be more stable than a primitive type alias? And if you're thinking like, yeah, my company, we're never going to do that, you might be right. Like you might not change int64, but this is just one example where you have to make a change that sort of has broad sweeping effects across the code base. And I guarantee you that every single one of you will need to do that at some point. Second, like C++ is just really complicated. And while there's this modern, this subset that we call modern C++, that's certainly simpler, our code bases are for the most part a mix of modern and legacy C++. And insofar as we have legacy code, we need to be able to understand that complexity. We can't just ignore it. And you know, as the language grows and as our code base grows, like we need a way to manage that complexity. There are a lot of tools here, you know, style guides, refactoring tools, improving compiler diagnostics. These are a few things that we know to be valuable, but I think there's a lot more that we can do there. And lastly, quick feedback is vital. Titus's talk yesterday had a nice picture, a thing he called shifting left. This idea that you really want to find out about problems as quickly as you possibly can, right? If you look at the issues that we discussed, the easiest ones were the ones where you had a compiler error, right? Like you write the problem, then you know about it immediately. As we push those further away, you know, to linker errors, to test failures, and ultimately like performance regressions, the costs of finding each of those grew dramatically. And the risks associated with, you know, what if this didn't work grew a lot as well. And this is why things like cling tidy and sanitizers and tools like that help us discover problems earlier are so vital. And with that, I want to say thanks and open up for questions.
With respect to the profile guided optimization,
Yeah.
how quickly would a new profile be created if you had like launched it? Like, I am assuming there'd be like they'd build a new profile based on the new thing and then like release it later.
Yeah. So you typically build a profile like from the old data and like the next release of your binary, depending on whatever your cadence is for releasing binaries. That profile gets applied for the next binary release. I think that depends, you know, a lot on who's releasing the binary, what their cadence is. But, yeah.
In doing these kinds of refactorings, one of the tools that I've used is to actually look at the generated executable and diff it between the two, and ideally end up in a situation where they're byte identical, except that you might have to, if you're changing symbol names, then you write a script that like filters that out and aligns things, for example. Were you ever able to use compiler output? Like, I might change the flags that I'm using to compile in order to turn off, you know, profile guided optimizations, for example, and probably some other things.
Yeah, this was not a thing we needed to do. I think if the profile guided optimization stuff didn't work, we'd really want to dig into the assembly and look at the output there. That's a really great way to ensure that your binary is like absolutely definitely going to be identical, right? If it's byte for byte identical, like you know you've got it right. We have, you know, really solid testing, and so that didn't seem necessary. When we know that, you know, all of the tests across our entire code base are passing, that's pretty good confidence that things are going to work.
Yeah. It seems potentially faster than testing because you can know without testing whether or not you changed something. But
Yeah,
you would have to have it set up. You have to have the tooling in place and the options in place.
You have to have that tooling in
Yeah.
place. And I think actually that gets to a point that I missed, is that I have a one button press to run all of the tests across the entire company. And so you have to set that up. But if you have that, it's this another amazing superpower where, yeah, I mean, the tests take a while to run, but, you know, compiling a binary also does too. And I run that, I, you know, go out to lunch and come back and I've run all the tests. So, yeah.
Okay.
It occurs to me that several of the root causes here are that we kind of violated half a single source of truth for like what is the definition, because like %LL was clearly like over specifying information that was already available there. Do we have other examples of like that as a pattern fitting into our like designs and refactoring plans?
Not that I can think of off the top of my head. I could imagine you run into similar problems with like const string ref versus string view. Another problem that comes up that I didn't end up mentioning here is that anyone can define an alias. And as long as they're all the same, everything is fine. And so like, yeah, we had this one sitting in integral types.h, but that was not the only type def or using decal that mentioned int64. And so we had, it was less than 100, but it was not significantly less than 100, I think, different definitions of int64 throughout the code base. And so you had, yeah, a lot of sources of truth for that.
Yeah. There's an idea in here that I think we should, yeah.
We should talk about it.
So was the string format work directly a result of like reaching that point where you had to fix all the string printfs, or was it just lucky that it was on the roadmap at the same time, or?
Yeah, so historically, this is before I started, right? I didn't design stir format. I wasn't the first person to sort of push on making those changes. Titus, do you know? This was...
I don't think it was solely inspired by this problem, but it was meaningfully inspired by this problem.
So Titus says, effectively, yes, it was meaningfully inspired by this problem.